Well, hello everyone. Thank you so much for coming to this week's SPAAM seminar. We have a bit of a math CDT overtake this week. So we're delighted to be joined by Sasha, who's going to be talking about what is the optimal way to lie. Take it away, Sasha.
Okay, so hi everyone. This is some work that I've been doing over the last 6 to 9 months with my supervisors, Susanna and Marie-Therese. I should also acknowledge Andrew because he did some key things at various points. So yeah, I'm going to talk a bit about opinion dynamics, optimal control theory, basically. Okay, so our setup is going to be, we have one opinion that we care about, and that's going to lie in some interval. We're going to say it's between -1 and 1. So if someone's got an opinion -1, that means they feel really strongly in a certain way. So say if our opinion is about like how much you like chocolate, then -1 would be you really, really hate chocolate. And +1 would be you absolutely love it. So that's kind of how it works. And it's modeled via a set of ODEs. This is the Hegselmann-Krause formation. And essentially what they do is that you move towards the mean of the people surrounding you. That's how your opinion changes in time. But that's according to some weighting, which is given by this function phi. And then the xj minus xi is just moving towards the mean. And that weighting is usually a function of distance. So if you're quite close to someone's opinion that you're talking to, you're likely to listen to them a bit more. So your opinion is going to change a bit more in that direction. So here are a few pictures showing that with different interaction functions, which is your weighting of how you're shifting your opinion. Yeah, usually you can see it's close to 1 for small distances and closer to 0 for large ones. But we're not actually going to do the interaction function being a function of distances because of differentiability issues. So instead, we're just going to keep it in this general phi of xi xj, which we're going to say is differentiable. Okay, and now I want to talk a bit about optimal consensus control. So optimal consensus control is basically concerned with, we want to steer the consensus of our population towards a certain value. And one way that this is done is via a leader and followers model, which is done by Albrecht and Peresci. So we have 2 groups. We have one of leaders who want to steer the other group, the followers, towards a particular goal opinion. And then we modify the Hegselmann-Krause formulation we saw on the previous slide for the setup. So and we add an optimal control. Okay, so the followers evolve according to this. So you should recognize these 2 terms really from the previous slides. So the first one is just a shift towards a mean follower opinion. Second is a shift towards a mean leader opinion. And then the leaders evolve according to shifting towards the leader's opinion, and then plus this control. And the control is basically the solution to some minimization problem, which wants to minimize the distance between the goal opinion and, say, the followers or the leaders' mean opinions. But I find this control a little bit difficult to interpret. Like, what does it actually mean? You know, you're just sort of forcing your opinion in some way. It's not very intuitive. So the way, the thing that I've been coming up with my supervisors in this, instead of having this sort of ominous control of having it have a direct interpretation, which is the lie. So here are the model assumptions for the lies. So we're going to assume that there's only one agent lying. I'm going to call it agent 1 because it's easier notationally, and we can do that without loss of generality. I'm going to say that the liar doesn't change his or her opinion in time. Their sole goal is to bring the population to consensus at their true opinion, which is x1, which doesn't change in time. And then the liar has these lies, which we call apparent opinions. So yi here is the lie that our liar tells to agent I. So there's n-1 of these. It's going to say 1 lie to agent 2, 1 lie to agent 3, etc., etc. And we're going to say that they all have to lie within our -1 sort of range. And instead of the Hegselmann-Krause having where you exchange the information of your true opinions, you're now going to be exchanging the information according to your apparent opinion. So mathematically, it's going to look a bit like this. So this is the opinion of a truth-telling agent, so just one of the normal ones. So this is a completely normal thing, normal Hegselmann-Krause. So we move towards the mean opinion of the agents surrounding you, the truth-telling agents. But then instead of starting from 1, we're starting from 2, because the contribution from agent 1 is here, and that's the lie. So this yi, we've just replaced x1 with yi, which is the lie that agent 1 is telling to person I. Then we've got x1 dot is 0, lie doesn't change their opinion in time. And then how are we going to define these yi's? So we're going to do that through an optimal control. We're going to choose yi to minimize this cost functional. So what this term here does is it encourages a control that moves the truth-telling agent's opinions closest to the goal opinion of x1. And t is just some arbitrary horizon in the future. And then we're going to add some regularization. So we're going to add some limits to what lies can be told. And those are going to be based on some social conventions, basically. Or we can have no regularization at all. Okay. So now I'm going to talk very briefly about how the optimal control thing is solved. I'm not going to go into very much detail on this. But basically, it's a discretize first and then optimize strategy. So first, we split the time interval into shorter time intervals, thanks delta t. Next, we're going to assume, next we're going to assume that the lie that you tell is constant on each of the time intervals. And finally, we're going to solve this problem. So yn is just a vector, dimension n-1. And then we're in the no regularization case here. So we've just got, we want to shift as much as we can towards a goal opinion, but you can say whatever you like as long as you stay within this interval. And then, yeah, subject to the dynamics of the Hegselmann-Krause model and this initial condition, which is just where you are at Tn. And yeah, what this integral means is that the lie can look into the future, basically, for one time step. It can plan, you know, if I say this lie, then this is how much I'll change the person's opinion by. And it can see that set of things and choose the best one, essentially. Okay, so yeah, you can solve that with standard sort of Hamiltonian arguments with ODE constraints. And then I'll show you some pictures. So first one is the dynamics. So this is what all the opinions are doing. So the red is a liar, everyone else is a truth-telling agent, just initialize them somewhere between -1 and 1. And you can see it there pretty quickly going down to the lie's opinion. It's been pretty successful. And then we should have a look at what the control is doing. So what are the actual lies that are being told here? And we get this sort of bang bang thing. So you're basically either saying that your opinion is 1 or -1 until the consensus point here. And then you say that it's your true opinion. And essentially why you do this is because there's no regularization. You can say whatever you want. So if you want to move someone's opinion as much as possible, and say the person you're talking to is up here, you want to bring them down to here. There's no point really saying anything in here because you're not going to move their opinion as much as if you say it's right down here. So you get this sort of, you say something really extreme in either way, because that's how you're going to shift their opinion the fastest. And, you know, this is kind of quite a nice strategy to think about. And, you know, you see it in real life. You know, it's kind of what George Osborne did when he was doing budgets and stuff. You know, he would say something leak something really insane to the papers. And then when his actual budget came out, it would be a lot less insane. And then everyone would go like, oh, it's actually really good. So it's kind of nice, and, you know, Trump does it too. It's kind of nice that you see that sort of qualitative behavior playing out with maths. And yeah, for those interested, here's the maths. So SIAM plus 1 depends implicitly on yi. And basically we solve this slightly using notation in that this will probably give you a number outside of the interval, so then you have to push it out onto the interval. That's fine. Okay, now we're going to add some regularization. So the first thing the standard thing in optimal control is to impose a cost on using the control. So here we're going to say that, you know, maybe there's some sort of conscience cost to lying a lot. So maybe we want to lie as little as possible. So mathematically, this looks like this. So the first term here is what we've seen before, encouraging agents towards your goal opinion. Our second term is penalizing the liar from deviating from the true opinion. And this little nu is a regularization parameter. Basically, a larger value of nu means that we care more and more about deviating from the true opinion. Okay, now pictures. So I've plotted this for a few different values of nu. You can see that for small nu, it's very quick because it's basically what we've seen before. The larger nu is not. It'll be easy to see what's happening with the control. Okay. So here we've got the bang thing that we saw before, the no regularization. And then as you increase nu, you see less and less variance around the liar's true opinion. So it's being forced to just tell the truth because of the regularization. And mathematically, this is what it says. And yeah, the important thing to note here is that basically it's a perturbation from the true opinion. If you use a very large value of nu, so we're in a regularization dominated scheme, this tends to 0. So we just get this. So being truthful, and then for smaller values of nu, we get closer to what we have in the regularization. No regularization case. Okay. Right, the next one I'm going to talk about is consistent apparent opinion. What we had before was a lot of this sort of jumping between -1 and 1. But, you know, if I tell Mark that I really, really hate chocolate, I tell Toby that I really, really love chocolate, then they talk to each other, they might smell a rat. So basically, now we want to minimize the different lies that we tell. So we've got a standard encouraging towards goal opinion, and then now we're penalizing the liar for telling different lies to different people. And then we've got regularization again. And here it basically does what you would expect. So for small nu, got our bang bang happening. And then for larger nu, it's just telling the same thing to everyone. It's gone to -1 here rather than anything else because our liar is at -0.25, so there's more agents above it than below. So it's better to say -1 basically. And mathematically like this. And again, if you think of it like a perturbation, you can see it's the perturbation from the mean of the lies that you're telling people. Yeah, okay. Final one, time consistent apparent opinion. So you can see in the previous slide, we have these big jumps, which again, might not be very true to life. You might not want to change your opinion loads in a single time step. That might look a bit suspicious. So what we do now is that we use an Euler discretization to write down the liar's change in opinion in time. We write out the optimal control problem now with encouraging towards goal opinion and penalizing the liar for changing their lie too quickly. You probably noticed that we've got an n-1, which means that we need an initial condition for y, because otherwise we can't work out y naught from that. So what we do is we just use, I think I use no regularization because we don't care about what we're saying to, about, you know, telling different things to different people. We're just, want the best. Okay. And then this is where we get some nice pictures. We get some oscillations, which is quite rare in opinion dynamics, so this was exciting. And then the control is doing a similar sort of oscillation in these two groups. And basically why we get these oscillations is because, you know, you see here it flattens out very, very suddenly. That's too big of a change in rate of change in opinion for larger values of nu. So you have to sort of oscillate around your goal opinion and get closer and closer and closer asymptotically. Okay, and then mathematically it looks like this. Perturbation from y n-1, which is what you would expect. Cool. Okay, right, quickly. We're going to go have a look at Boltzmann type. This will have some scary looking equations, I'm sorry. Okay, so first thing we're going to do is introduce opinion densities for the truth teller and the liar. So these are normalized densities. Normalized densities on your interval. So it tells you, the probability of being at a certain opinion at a certain time. And for the truth tellers, we normalize that to 1. For the liars, we normalize it to some rho, less than 1. This is a parameter that we want to be able to vary. It basically talks about the relative influence of the liar. So how much the liar influences the population compared to how much the truth tellers influence each other. But we know the density of the liar, because the liar doesn't change her opinion in time. It's just at x1, so it's this delta function. And then times rho, so that we get the appropriate normalization. Okay, and we're going to do a couple of extra additional assumptions. First thing we're going to do is we're going to assume that 5xi xj is just 5xi. So your how you're interacting with people only depends on where you are in the opinion spectrum. It's a bit limiting, but it makes the analysis a lot nicer. So that's what we're doing. And then we're going to take the first regularization we saw, where the liar wants to stay close to its true opinion. And so y is going to look like that. And then, yeah, the xi plus 1 has some implicit dependence. So, yeah, you can rearrange it. It's fine, basically. And then that's going to help us when we do the Boltzmann type description. The Boltzmann type description sort of comes from the realm of natural gases and things. So what we're essentially saying is that as the population size of our microscopic model tends to infinity, the description, we can sort of describe the interactions as being like the interactions between random gases. So particles hit each other at random in random gases, and we're saying the same thing here, basically, that people interact at random. And this is the Boltzmann equation. Yeah. The first term on the right represents interaction between truth tellers. Second term, the interaction between truth tellers and the liar. And then this phi is just an arbitrary test function we do for weak formulations of PDs and things. And then these are what the Qs are. They look really horrible, I'm sorry. But basically, we're integrating over all interactions between truth tellers and truth tellers, and interactions between truth tellers and liars. And what these X stars are is that, so that's the result of a microscopic binary interaction between truth tellers and between a truth teller and a liar, respectively. So we're going to add a bit of noise to that. And yeah, we've got an exact form for our control, so we can substitute it all in, and that's all nice. Yeah, these eters are rates of interaction, so we can mess around with that a bit. And then the angular brackets are just expectation after we've added noise to the binary interactions. Okay, and then we can take a quasi-invariant limit, and it's all a bit messy. So I'm not going to show you that, but at the end you get a nice Fokker-Planck equation, which is a bit long, I'm sorry. And so term by term. First term is just about time evolution of the truth teller's density. The final term is just our diffusion from the noise that we added in our microscopic binary interactions. And then the first drift term is a shift towards the mean opinion of the truth tellers, which you can see here. So yeah. And then the second term is a shift towards the liar's opinion, so x1 minus x. And then that's proportional, well, to 1 over your regularization. Okay, so there are some stationary solutions do exist for very nice functions of phi and nice functions of the diffusion. And then, but to get any idea of what's happening at earlier time steps or the evolution, or for more complicated interaction kernels and things, we want to discretize. So we use a finite volume discretization to see some behavior at earlier times. This is kind of what happened. It's pretty much what you would expect. This is a very, very simple case. So we start at this symmetric initial condition, and then as time increases, you get this, you get a peak. And I think that's pretty much a steady state solution. Yeah, 2 equals 5, it will be. And yeah, I mean, it's slightly offset. I've put the liar's opinion here to be 0.5. You get this slight offset of the peak, but that's just because of the diffusion. That's nothing to worry about. The mean is still. So yeah, in conclusion, hopefully I've semi-convinced you that this is a slightly more realistic framework for considering optimal consensus control. We've compared some different regularization strategies, each rooted in a social convention. There's still some stuff to do. So sparse control. So the liar wants to decide who they will have the most influence on by lying to them. Mean field limit, which would be nice because then we can derive controls from a PD rather than using the ODE controls into the PD. Yeah. And then there are some bigger questions. So how can we model the liar being found out? And what happens when the liar is found out? You know, it's notoriously bad to do like negative forcing in opinion dynamics because you just get unbounded things. So that will be hard. And then the last thing is, you know, that so far we're kind of helping out the bad guys. We're telling people how to lie better, whereas what might be good would be to find ways of disrupting this consensus control of, you know, yeah. So yeah, that's on my conscience. But yeah, that's all I want to talk about. Thank you.